Here we present Bridging the Imitation Gap by Adaptive Insubordination. This is a collaboration between researchers at the Allen Institute for AI, the University of Illinois Urbana-Champaign, and the University of Washington. In this work, we consider a phenomenon we observed in practice. Even when optimizing perfectly, experts that are too smart can fail to teach their students optimal policies. As an outline of this presentation, we will first define this phenomenon, which we call the imitation gap. We will then introduce our advisor methodology that adaptively weighs imitation learning and reinforcement learning losses to bridge this gap. Finally, we summarize our experimental results, which show that advisor can bring drastic improvements over competing baselines in tasks set in grid worlds, continuous multi-particle environments, and even in high visual fidelity simulators. Consider this simple grid world set in the mini-grid environment. The red triangular agent must navigate its way to the green goal. A well-meaning expert sees this environment state and says, obviously, move forward. But this starting position of the agent is only one of many. For instance, the agent could be facing the left. Here the expert says, obviously turn to your left. Similarly, the expert might say that turning right or left are both correct, or that turning right is the optimal strategy. But now consider what our student observes in each of these environment states. Rather than observing the full environment state, student agents frequently only have access to partial egocentric observations. In each of these states, the expert tells the student to do different things despite, from the student's perspective, all the states looking exactly the same. More formally, we say that the observation seen by the agent is filtered by a filtration function f. In this example, this filtration function maps 4 distinct environment states to the same partial observation O. Proposition 1 in our paper shows that in these cases, the student's policy is an average of the teacher's. Formally, let pi il be the policy among all possible student policies that minimizes the cross-entropy loss between itself and the expert. We show that pi il then equals this conditional expectation. To get some intuition, let's decompose this equation. We have that the student policy minimizing the cross-entropy loss evaluated at a partial observation equals the average of the expert policy evaluated over all environment states which correspond to the same partial observation. In our original example, this means the student would never learn to consistently move in one direction or another. Thus, in many realistic partially observed settings, even with perfect optimization, it is possible that a student will fail terribly in imitating the expert. So what are some potential solutions to this? We can design experts that operate on exactly the same observations as our student. For such experts, there is no imitation gap, but they can be expensive to obtain when using human annotators or nearly impossible to code. If it was straightforward to write a function that maps images and goals to expert actions, then we wouldn't need RL agents at all. Alternatively, we can develop more sophisticated memory architectures. As the agent explores the environment, it can then patch together its partial observations until it has a comprehensive understanding of the full environment state. Once it has such an understanding, it will, by definition, have enough information so that it can imitate the expert. Unfortunately, the imitation gap remains during this exploration phase, which harms training. Moreover, building these memory architectures brings its own collections of technical challenges. We instead propose the adaptive insubordination methodology, or advisor. Intuitively, we would like to imitate the teacher when we have enough information to do so, and otherwise ignore them. In practice, this means we wish to adaptively reweigh imitation learning and reinforcement learning losses at every step. Namely, we'd like our agent's loss at a state S to be a weighted combination of the imitation learning and reinforcement learning losses with a weight function W. We would like this weight function to equal 1 for states where the student can imitate the expert, and otherwise equal 0. This raises a critical question. How do we estimate this weight function W? Our solution to this question is to create an auxiliary policy which is used only during training. This auxiliary policy attempts to imitate the expert by using only IL losses. For states where the auxiliary policy is successful in imitating the expert, we set the weight function to be near 1, and when it fails, we set it to be near 0. In practice, this idea is easy to incorporate into any actor-critic framework. In our experiments, we simply add an additional policy head to our network and train this policy purely by imitation learning. This auxiliary policy is then used to define the weight function, which is used in our advisor loss that trains the true policy of our agent. Finally, we provide a brief summary of our empirical results. In our experiments with discrete grid worlds, we exhaustively evaluate 15 reinforcement learning and imitation learning baselines across 9 tasks, following best practices to control for the impact of hyperparameter tuning. This table summarizes the performance of our advisor-based methods when compared to baselines across our 9 tasks. Notice that our advisor-based methods perform well across the board and are frequently the only methods to achieve non-trivial performance. We also evaluate advisor on tasks with continuous action spaces and in tasks set in visually realistic simulated environments. In these tasks, we again see that advisor outperforms and that the difference in performance is only more dramatic in the low sample regime. In summary, if imitation learning isn't working for you, your expert might be too smart to teach. If that's the case, you should treat them as an advisor. Listen to them when they're helpful, ignore them when they're not.